Hi, I'm Katie Winkle from the Bristol Robotics Lab, and I'm going to talk to you about our work on in-situ learning in socially assistive robotics. So let's take an example application of socially assistive robotics, personal training or helping with exercise. This is what you might expect to see in a training session, with the instructor giving some explanation or direction to the client. But we also see a lot of this, off-topic social interaction. A previous study with therapists identified that this type of interaction is intentional and it's designed to keep the client engaged in their exercise, but also very intuitive, making it quite hard for us to design and automate the equivalent for socially assistive robots. Previous work by Emmanuel Senft demonstrated how you could extend on the Wizard of Oz setup to actually move your robot towards autonomy by capturing input data and combining it with the wizard's control of the robot to train a machine learning algorithm. Over time, the robot learns what to do from the wizard and starts to make its own suggestions that the wizard can accept or reject for a further learning input. In this work, we build on that approach to have an expert involved in the design and automation of a socially assistive robot. So first, you co-design the robot actions and input space with the domain expert. Then you co-design a teaching interface that the expert can use to trigger those actions and to respond to suggestions when the robot starts making them. And then finally, you have the domain expert teach the robot through the machine learning in the wild deployment. We apply this approach to design of a robot fitness coach to support the NHS Couch-to-5K programme, a longitudinal, monotonous exercise programme where social interaction is going to be vital to keeping people engaged. We suggest there are 4 key categories of input data a socially assistive robot might consider. Firstly, the task state, so just information about the current task, whether you're running or walking, how far through the session you are, and things like that. Then there's task performance, so how well is the user actually doing? For us, that was just simply speed. Dynamic task engagement, so right now, how much effort is the participant putting in? And for us, that was heart rate and self-reported effort and facial expression. But also a more static task engagement, so what's their overall motivation to be here and their engagement with the programme? And finally, personality scores, because we expect that social interaction needs to be personalised to the user. We then identify 3 key types of output the robot should have. Task actions, so obviously in our case telling them whether to run or walk. Supporting actions, which is where much more of the social interaction comes in, so that could be giving encouragement, but it could also be checking how exerted they are, or maybe having a celebratory animation. Finally, you might want to control lower level behaviours of the robot. So we adjusted eye colour, but you could also adjust proxemics or other non-verbal interaction behaviours. Across all of these actions, you can then apply a style: positive, challenging, sympathetic, or neutral. Overall then, actions are made up of an action type and a style. So for example, a sympathetic run might try to say, come on, you've got this, now we need to run again. Having designed the system, we then deployed it in a real university gym for 3 months. We put 10 participants through the programme, of whom 1 dropped out. We ran over 200 sessions in total, about 30 of which were autonomous, and we also compared that autonomous robot to a heuristic-based system, also designed by the fitness instructor. The results show that the autonomous system acted very similarly to the system when it was supervised by the instructor, and that both of these were very different to the behaviour of the heuristic system, even though those heuristics were designed by the same expert. And that's mostly because there's some actions for which he just couldn't write a heuristic. For example, when to tell a joke. If you get that wrong, it's really bad for your interaction. The results also showed that the fitness instructor used the system to create personalised behaviour for each participant, and the autonomous system successfully learned this and replicated it. This again contrasted with the heuristic system, which for these 2 participants created pretty similar behaviour. So to conclude, we've shown that interactive machine learning can be a form of participatory design where you can have a domain expert involved directly in robot automation. We showed that our system successfully learned what actions for who, but we did have some issues with repetition. The robot didn't learn that sometimes it's okay to do nothing. Just want to say a quick thank you to the people at UE Centre for Sport who made this happen. Thanks.